The geological record of our planet reveals an intricate tapestry of climate transformations spanning vast epochs. Temperature oscillations, radiation variations, and shifts in atmospheric chemistry have acted as evolutionary catalysts for certain species, while serving as extinction triggers for others. Throughout history, mass extinction events have eliminated as much as 90% of Earth's biodiversity, pushing planetary life systems toward total collapse. Scientific documentation confirms 5 such catastrophic episodes across the last 500 million years. Current data indicates we are witnessing the onset of a 6th extinction event, unprecedented in its velocity and comprehensively monitored. What forces are driving our planet's current trajectory, and what mechanisms underlie the rapid deterioration of Earth's biosphere? Let us examine the evidence. Celestial influences. The climatic patterns of Earth, much like those governing any astronomical body, emerge from an intricate web of interconnected variables. External drivers include solar radiation fluctuations and orbital perturbations that follow predictable cycles. Internal mechanisms originate within Earth's own dynamic systems. Understanding current trends and projecting future scenarios requires examining our planet's climatic evolution across tens of millions of years. This temporal perspective reveals the mechanisms that have reshaped Earth's surface and the variables governing climatic transitions. The temperature record displayed here chronicles our planet's thermal history across 500 million years. Through systematic analysis of geological evidence from global excavation sites, researchers have reconstructed detailed climate profiles for each geological period. This comprehensive view reveals a pattern: extended phases of elevated temperatures punctuated by briefer cooling intervals. These cooler epochs, termed glacial periods, featured reduced atmospheric moisture, lower average temperatures, and persistent polar ice formations, conditions mirroring our current climate state. Each planetary temperature shift represented a survival challenge for Earth's biological communities. Many species failed to adapt to these environmental pressures. The Cretaceous catastrophe. Approximately 66 million years ago, a colossal asteroid measuring 6 miles across hurtled toward Earth at tremendous velocity. The cosmic projectile breached our atmosphere within moments, delivering a catastrophic impact to the planetary surface. The resulting detonation unleashed energy equivalent to millions of thermonuclear devices, generating seismic disturbances across the globe. Powerful shock waves displaced massive rock formations, excavating a crater spanning approximately 110 miles. Debris fragments were ejected beyond atmospheric boundaries into space. These materials subsequently rained down across thousands of miles from the impact zone, igniting extensive wildfires. Research indicates the initial shock waves propagated globally, triggering seismic activity in Earth's most distant regions. Massive oceanic waves devastated continental margins, advancing hundreds of miles inland and obliterating everything in their wake. Approximately 15 trillion tons of particulate matter and combustion residue entered the atmosphere, with global air currents distributing this material planet-wide. Earth's solar radiation reception decreased dramatically for extended periods, precipitating severe cooling. Scientific analysis demonstrates that for no less than 16 years following the impact, global average temperatures stabilized near 37 degrees Fahrenheit, representing a 20-degree reduction from contemporary levels. This temperature depression caused widespread plant mortality across terrestrial and aquatic ecosystems, creating food scarcity throughout animal populations. Nearly all organisms exceeding 55 pounds in body mass vanished, including terrestrial dinosaurs and marine reptiles. Some species perished during the initial catastrophe, others succumbed to subsequent environmental degradation. These events initiated the Cenozoic era, marking a fundamental transition in planetary history. Recovery and thermal maximum. The subsequent decade spanning 10 million years, designated the Paleocene epoch, witnessed Earth's gradual recovery from this devastating event. Atmospheric volcanic debris slowly dispersed, allowing temperatures to return to habitable ranges. Life systematically recolonized vacant ecological niches. However, the planet now supported entirely different organisms, flowering plant species, mammalian fauna, and avian populations. The Paleocene's conclusion featured rapid temperature escalation connected to intensified tectonic processes. Volcanic activity throughout the North Atlantic region released massive quantities of methane and carbon dioxide into the atmosphere, elevating concentrations to 2,000 parts per million, 5 times current atmospheric levels. This warming phase marks the onset of the Eocene epoch, commencing approximately 56 million years ago and persisting for roughly 22 million years. Throughout this extended period, global average temperatures exceeded modern levels significantly, occasionally reaching 82 degrees Fahrenheit. Fossil evidence indicates that Eocene climate conditions were predominantly tropical across most continental areas. Extensive broadleaf forests extended to Arctic latitudes. Documentation confirms that palm species flourished in regions now comprising Europe, alongside thermophilic reptilian populations. The primary driver of these conditions appears to be optimal continental positioning. North and South America remained separated by extensive marine channels during this era. Africa and Eurasia had not yet converged. Consequently, equatorial ocean currents and atmospheric circulation patterns moved freely around the globe, maintaining relatively uniform heat distribution. Furthermore, organic decomposition processes sustained elevated atmospheric carbon dioxide concentrations, reinforcing warm climate conditions. These favorable environmental conditions enabled mammalian evolution from small marsupial forms inhabiting burrows and forest canopies to massive species weighing multiple tons. This period saw the emergence of ancestral lineages for most contemporary mammalian groups, early primates, artiodactyls, and rodent species. The Great Cooling. Nevertheless, planetary conditions continued evolving through gradual but persistent changes. Aquatic fern proliferation in northern marine environments gradually reduced atmospheric carbon dioxide levels, initiating steady cooling trends. Around 34 to 35 million years ago, temperature records show an abrupt and dramatic decline. This transitional period between the Eocene and Oligocene epochs featured multiple significant geological developments. Initially, continental collisions elevated massive mountain systems including the Himalayas, Alps, Carpathians, and Appalachians, fundamentally altering atmospheric circulation dynamics. Additionally, paleontological analysis reveals widespread adoption of C4 photosynthesis among plant communities during this time frame. This metabolic innovation proved substantially more efficient than preceding photosynthetic mechanisms, gradually increasing atmospheric oxygen concentrations by 2 to 3 percentage points to modern levels. Conversely, carbon dioxide content declined markedly, reducing greenhouse warming effects and driving global temperature reductions. Furthermore, tectonic movements severed the terrestrial connection between South America and Antarctica. Earth's rotational dynamics subsequently established a continuous oceanic circulation system, forming a cold current ring around the planet's southernmost continent. Atmospheric patterns similarly created an impermeable barrier preventing warm air masses from reaching Antarctica. Continental temperatures consequently decreased rapidly. By the Oligocene's end, Antarctic vegetation had been completely replaced by expanding ice formations. These combined developments established the Oligocene epoch, spanning approximately 11 million years, characterized by relatively consistent, arid, and cool climate conditions, though still notably warmer than present-day temperatures. Miocene climate crisis. This cooling trend persisted into the subsequent Miocene epoch. However, around 14 million years ago, temperature records reveal another dramatic cooling event. This phenomenon, termed the Middle Miocene climate crisis, resulted from two converging factors. Primarily, Earth's orbital dynamics again entered the cooling phase of Milankovitch cycles. These cycles represent periodic variations in solar energy reception based on Earth's axial orientation and orbital parameters. When orbital eccentricity reaches maximum values while winter solstice coincides with perihelion, planetary climate becomes substantially colder. This precise configuration occurred 14 million years ago during the Middle Miocene crisis. The resulting temperature reduction caused forest contraction, with grassland and savanna ecosystems expanding into former woodland areas. This transition promoted rapid proliferation of C4 photosynthetic plants, which demonstrated superior resilience and competitive advantages. Consequently, atmospheric carbon dioxide concentrations dropped precipitously, intensifying cooling trends. Understanding this period's ecological dynamics requires recognizing that savanna ecosystems represent highly productive biological systems. Individual square miles of grassland generated approximately 4,000 tons of organic matter annually, nearly equivalent to the biomass of resident animal populations. Nutrient-rich grasses with brief life cycles provided herbivore sustenance while facilitating rapid nutrient cycling, particularly carbon processing. Expanded grassland coverage therefore reduced atmospheric carbon dioxide and accelerated temperature decline. Global average temperatures decreased approximately 11 degrees Fahrenheit across several million years, dropping from 63 degrees Fahrenheit to 52 degrees Fahrenheit. This climatic shift eliminated most large fauna from previous periods. The era's most characteristic animals included diverse proboscidean species and early equine ancestors known as hipparions. Dominant predators included large canids and hyenodons, some reaching half-ton body masses. Pliocene glaciation. Temperature data clearly demonstrates that following the Middle Miocene crisis, Earth entered sustained and irreversible cooling. This transition accelerated polar glacier development, beginning approximately 8 million years ago. Antarctic ice sheets expanded dramatically. Permanent ice coverage established itself across the Arctic Ocean. Greenlandic forests disappeared rapidly, yielding territory to advancing glaciers. The most significant challenges remained ahead. Around 2.6 million years ago, cooling rates accelerated markedly. Continental drift and declining sea levels created the Panamanian Land Bridge, permanently blocking oceanic circulation between North and South America. Pacific equatorial waters could no longer intermix with Atlantic currents. Atlantic Ocean temperatures began systematic decline. Simultaneously, the Rocky Mountain system, having achieved substantial elevation by this period, began intercepting warm atmospheric flows, further disrupting global heat distribution. Seasonal temperature variations across continental areas intensified considerably, while glacier expansion rates increased substantially. During this same time frame, the Gauss-Matsuyama magnetic reversal occurred, causing Earth's magnetic poles to exchange positions. For 15,000 years, planetary magnetic field strength decreased to approximately 1/4 current intensity, contributing to multiple marine species and algae extinctions. These climatic changes combined with magnetic field disruption marked the beginning of the Pleistocene geological period. Ice Age dynamics. Ice formations became the Pleistocene's defining characteristic. These glacial systems alternately advanced across up to 30% of continental surfaces, then retreated toward polar regions. However, complete ice disappearance never occurred. Early Pleistocene periods exhibited remarkable cyclical consistency. Cooling and warming phases alternated at 41,000-year intervals. This periodicity precisely matches Milankovitch cycle patterns. Therefore, natural orbital variations are considered the primary driving mechanism. Glacial movements and climate fluctuations inevitably influence flora and fauna, reshaping planetary biological communities. Global cooling prompted many herbivorous species to develop insulating fur while increasing body size for cold adaptation. This evolutionary pressure produced mammoths, mastodons, woolly rhinoceroses, and other massive herbivorous species. Predatory species similarly increased in size. North American ecosystems supported giant polar bears, formidable creatures whose calculated weight could reach 2,650 pounds, representing 3 to 4 times the mass of contemporary relatives. Southern regions hosted dire wolves, approximately double the size of modern wolf species. Evidence suggests these predators operated in coordinated groups of 3 to 4 individuals, employing sophisticated hunting strategies capable of bringing down bison. Approximately 1 million years ago, glacial periodicity became disrupted. Cooling cycles lost their regularity, with average durations extending to 100,000 years. Temperature variations intensified alongside increased ice thickness. This transformation, designated the mid-Pleistocene transition, remains incompletely understood. The most supported hypothesis suggests that previous glacial activity removed regolith layers covering bedrock across northern latitudes. Subsequent ice formation occurred on less conducive rock surfaces, such as granite and basalt, disrupting established cyclical patterns. Alternative explanations include Bering Strait closure resulting from sea level reduction and glacial expansion. This event, occurring approximately 900,000 years ago, prevented Pacific cold water circulation into Arctic regions. The change produced additional temperature reductions and intensified cooling trends. Throughout the Pleistocene, early human populations gradually dispersed globally. Research has identified evidence of multiple large-scale migrations alongside numerous smaller population movements. Operating as nomadic foraging and hunting societies, ancient communities explored new territories, competed for resources, interbred, and separated, generating dozens of distinct human variants. Some lineages left only skeletal remains and abandoned settlements. Others achieved greater success. These successful populations represent the ancestry of all contemporary humans. Terminal Pleistocene. The late Pleistocene period, alternatively termed the Turantian stage, commenced 129,000 years ago and persisted for 117,000 years. This time frame represented maximum cooling intensity and largest glacial formations. Through intense survival competition, Cro-Magnon populations, direct ancestors of modern humans, eliminated or absorbed all alternative human communities. Seeking refuge from environmental hazards, ancient populations expanded beyond Eurasian and African boundaries. A terrestrial corridor at the current Bering Strait location enabled multiple migration waves into North America, establishing the ancestral populations of numerous indigenous American tribes. Concurrently, thousands of miles southward, declining sea levels created access routes to Australia. Consequently, approximately 50,000 years ago, human populations reached this isolated continental system. Lacking comprehensive environmental understanding, early humans could not anticipate long-term consequences of their activities and maintained exploitative relationships with natural systems. Australia presented newcomers with a verdant paradise containing abundant vulnerable prey. Unfamiliar with human presence, slow-moving and awkward giant marsupials, including diprotodons and procoptodons, could not effectively resist these intelligent and numerous new predators. Within merely 10,000 years, most Australian fauna exceeding 100 pounds had been eliminated. Hunting strategies employed by indigenous populations included systematic vegetation burning, creating extensive forest fires. Most game acquired through these methods was ultimately wasted. Animals perished in fires alongside forest destruction, leaving behind semi-arid landscapes supporting only sparse grasses and hardy shrub vegetation. Australian climate conditions are characteristically dry, with soils lacking substantial fertility. Therefore, destroyed forest ecosystems cannot naturally regenerate. Consequently, when sea levels subsequently rose, Australian populations found themselves confined to a degraded continent incapable of supporting expanded human populations. Following violent conflicts and extended famine periods, population levels stabilized at sustainable numbers. However, pathways towards civilization remained inaccessible to these isolated communities. Agricultural Revolution. Pleistocene conditions concluded approximately 11,700 years ago when the final cooling period ended, glacial systems retreated, sea levels increased 115 feet, and unique biomes developed across various Earth regions. The most renowned examples included the Nile Valley and Mesopotamian regions. However, numerous additional favorable areas emerged. Abundant water resources and fertile soil conditions promoted extensive cereal cultivation, producing seeds with exceptional nutritional content. Adjacent communities no longer required nomadic food-seeking behaviors. Natural productivity exceeded population requirements. These conditions enabled sedentary gathering practices, which subsequently evolved into agricultural systems. Agricultural production requires processing and storage capabilities. These necessities stimulated construction techniques and ceramic crafts, followed by metallurgical developments. These innovations established the foundation for earliest civilizations. Technological complexity gradually increased while human environmental impact expanded. Forest clearing, agricultural expansion, irrigation infrastructure, toxic industrial practices, and urban development caused progressive natural degradation around human settlements. Nevertheless, these changes remained geographically limited for extended periods, requiring centuries to become permanent. Industrial transformation. Conditions changed rapidly beginning in the 18th century with Industrial Revolution onset. Expanding manufacturing facilities and factory construction produced accelerated carbon dioxide emission increases. Additional atmospheric pollutants included sulfur oxides and various compounds that reacted with water vapor to form corrosive acids. These aggressive chemicals accumulated in soil and water systems, gradually rendering them unsuitable for biological processes. Emission growth accelerated particularly during the latter 20th century. Thousands of power generation facilities and industrial plants emerged globally, while improved living standards and technological advancement promoted widespread automotive transportation. Individual passenger vehicles might appear to generate limited waste products. However, daily carbon dioxide releases average approximately 33 pounds per vehicle. Annual emissions total roughly 6 tons per automobile. Considering approximately 1 billion passenger vehicles and 400 million commercial trucks currently operating worldwide, total emissions clearly reach billions of tons. Thermal power plants and industrial facilities contribute even more substantially to planetary pollution. During 2022 alone, human activities released approximately 38 billion tons of carbon dioxide into the atmosphere. Some claim this quantity appears insignificant compared to volcanic emissions. However, this represents a dangerous misconception. Scientific data demonstrates that volcanic activity contributes only 260 million tons of atmospheric carbon dioxide annually, approximately 150 times less than anthropogenic sources. Atmospheric CO2 concentration data shows current levels have reached 400 parts per million, roughly 35% above any previous point in human history. Similar atmospheric carbon dioxide concentrations last occurred approximately 5 million years ago, preceding the global glacial period. Most concerning is that current levels developed within less than 100 years, with continued growth. Environmental consequences. What dangers does this process present? Primarily, increasing global temperatures accelerate glacial melting, changes already underway. Greenland's largest glacier, Jakobshavn, has quadrupled its melting velocity compared to early century rates. Annual retreat distances range from 2 to 4 miles inland. Recent years have shown some deceleration, though scientists maintain this represents temporary stabilization. Current warming also triggers permafrost melting. This process renders countless northern latitude settlements uninhabitable. Marine industries experience severe disruption from unstable ice conditions. Permafrost functions as a massive planetary refrigeration system containing billions of tons of frozen organic materials. Melting releases this matter for decomposition, producing carbon dioxide and methane that further accelerate warming processes. Calculations indicate complete ice cap melting would raise sea levels 217 feet. Major cities including New York, St. Petersburg, Shanghai, London, and numerous others would experience complete or partial submersion. Entire nations and regions would disappear. Examples include the Netherlands, Polynesia, and the Yamal Peninsula. Millions of square miles of coastal areas would become submerged. The most productive agricultural lands and densely populated settlements would face irreversible destruction. Rapid warming will degrade countless additional territories. Forest fire frequency will increase while desert expansion accelerates. These combined factors inevitably direct global systems toward another mass extinction event. This process has already commenced. Approximately 1,000 large animal species have vanished over the past 500 years. More than 35,000 vertebrate, insect, and higher plant species currently face extinction threats, including 40% of amphibian species and 25% of mammalian species. Critical human-dependent species are included, such as banana plants and honeybee populations. Their loss could permanently transform our world in decidedly negative ways. Contemporary humans regard themselves as intelligent and civilized. Nevertheless, their behavior sometimes demonstrates even greater recklessness than ancient populations. Unlimited ambitions, profit-seeking, and power pursuits have repeatedly generated ecological disasters. This pattern indicates that modern humans have not advanced significantly beyond Australian Aboriginal communities who systematically destroyed their inherited fertile environment. Without developing careful stewardship of our planetary home, human civilization will conclude ingloriously within Earth's boundaries, relegating distant stellar exploration to permanent fantasy. Colleagues, climate change questions inevitably impact every individual. Therefore, please share your perspectives through comments. We shall reconnect soon.